Hello everyone. In today's video, we are going to start talking about some organic reactions. So we're going to start with reactions at the carbonyl group. So before we begin, we need to understand equilibrium at a very basic level. So what's equilibrium? Well, for any reaction, you have reactants and products, and your reactants are on the left, where products are on the right. So reactants are converted to products, and that's called the forward reaction. And when you do it the other way around, it's called the backward reaction. So they are converted, reactants are converted to products and vice versa at the same time, but different rates depending on the concentration of each of the species as well as their individual reactivities. So there must be a point of balance where the rates of the forward and backward reactions are equal. And what happens at this point is called equilibrium, where the ratio of concentration of reactants and products is called the position of equilibrium. So in textbooks, different textbooks might have different definitions of position of equilibrium. That's basically how favorable the reaction is, where the balance point is. So that's called the position of equilibrium. So at equilibrium, making the reactants more concentrated will cause the forward reaction to overtake the backward reaction because the rate of the forward and backward reactions depends on the concentrations of the reactants and products. So by making the concentration, by changing the concentration of either the reactants or the products, the rate of one of the reactions would change. And because of that, more product will be converted to reactant or the other way around, and this will cause the position of equilibrium to change as well. But eventually, a new position of equilibrium will be established where the concentrations kind of strike a point of balance again so that the rates of the forward and back reactions are equal. So when we say reversibility or favorability of a reaction, that basically means where the position of equilibrium lies under normal conditions, such as those used in lab experiments or reactions and products, which is also known as yield. So, for example, in lab, when we add a dilute acid to a dilute base, because this reaction is extremely favorable, we would usually get a neutralization reaction. So you usually don't see water breaking down into H plus and OH minus. Instead, the H plus and OH minus would combine to form water. So that's what you mean by very favorable. However, when we add, let's say, nitrogen and hydrogen under room temperature and pressure, they don't react that extensively to form ammonia, and that's what we mean by a less favorable reaction under normal conditions. Of course, you might know that when we add a lot of pressure to the nitrogen and hydrogen, the ammonia will be formed in a more favorably, and the yield will be higher. So um, yeah, so the favorability and reversibility also depends on what conditions you use. But normally, when we're talking about favorability, we are just talking about those that are possible in lab experiments or lab conditions. So yeah, so that's what we mean by reversibility or favorability. So now that we are clear on what equilibrium means, we are going to move on to talk about nucleophilic attacks at a carbonyl group. So why do we call it nucleophilic attack? Well, because oxygen is much more electronegative than carbon, so the carbon will carry a partial positive charge because the bond pair between the carbon and oxygen is much more attracted to the oxygen than the carbon, causing the carbon to carry a partial positive charge because while it still attains while it still has the lone pair, sorry, while it still has the bond pair with it, so the bond pair didn't go to the oxygen completely. The bond pair is much more closer to oxygen than it is to carbon. So the carbon sort of has a lack of electrons, so to say, and so it carries a partial positive charge because electrons are negatively charged. So this carbon center is thus electron poor and is electrophilic because it's electron poor, so it loves electrons. Because positive attracts negative, so it's electrophilic, and it would like to attract electron-rich nucleophiles. So uh, nucleophiles are basically electron-rich species, and because of this, because negative attracts positive, it attracts electrophiles. So in a lot of organic reactions, you see you are a lot of them will be nucleophilic and electrophilic reactions. So where the nucleophile and electrophile attract each other. So why do we call attacks at the carbonyl group nucleophilic attacks? Well, we are not talking about carbonyl group when we say nucleophilic. The carbonyl group is electrophilic. Instead, we are naming the attacks according to the species that attacks that particular group. So for example, nucleophiles attack the carbonyl group, so we call it nucleophilic attacks. So I would like to circle back to the point I made just now about the bond pair. So when you have a covalent bond or a largely covalently bonded pair of atoms, well, the carbon and the oxygen, so they share a pair of electrons. Actually, they share two pairs of electrons, but let's just talk about one of the pairs. So they share a pair of electrons, and this pair is located closer to oxygen than to carbon. So, if in an extreme case, the pair of electrons is extremely close to one of the atoms, well, that's what we call ionic bonding. So, for example, when you have sodium oxide, because oxygen is so much more electronegative than sodium, because sodium is a metal and oxygen is one of the most electronegative elements after fluorine. So the difference in their electronegativity is so large that the bond pair will be pulled towards the oxygen, and the oxygen sort of has stolen the pair um from sodium, and because of that, because of the because usually in bond pair, one electron comes from each atom, right? So in a sodium and oxygen pair, one of it actually comes from sodium. So oxygen, so they say, stole the that one electron from sodium, and so it has the electron pair to itself. It doesn't want to share it with sodium, so we call that ionic bonding. So when we talk about bonding, in a lot of cases, the definition isn't that clear cut. So where do we draw the line between ionic and covalent bonding? The thing is, there are almost no absolutely ionic or absolutely covalent bonding. It's usually on the spectrum. So in the case of the CO bond, it's usually considered covalent bonding, while in the case of, let's say, sodium oxygen bond is considered ionic. However, in a lot of cases, for example, the cases involving lithium, which is somewhat it's quite electronegative for a metal. When it's bonded to a metalloid such as boron, the case is somewhere in between. So those are the less clear-cut cases. So yeah, and we will encounter them when we study organic chemistry. And yeah, just take note that there's no clear cuts between ionic and covalent. So, circling back to the CO double bond, to the carbonyl group, the nucleophile may attack the electrophilic carbon, causing the CO pi bond to break towards oxygen. Because remember, oxygen is more electronegative, so it's more stable to bear the negative charge, the full negative charge this time round. So, the lone pair would prefer to go towards O. So the lone pair used to be a bond pair, but because it has gone up to the oxygen atom, it's now considered a lone pair. So in this case, the carbon here is partially positive charged, or this oxygen has a partial negative charge. So this bond pair would prefer to break towards oxygen than towards carbon. So here the nucleophile, because carbon can only form 4 bonds, so here the nucleophile with its lone pair of electrons, so it's electron rich, will attack this carbon center. And because a carbon can only have four bonds, this bond needs to break, and it will prefer to break towards oxygen. So in this case, you might think, hey, this oxygen is partially negative, has a partial negative charge. Why wouldn't it react with an electrophile? Well, this is um because this the attraction of this let's say this oxygen towards electrophiles is much weaker than the attraction of this partial positive carbon towards nucleophile. So the nucleophile would attack at this place instead. So after this attack, you would have a tetrahedral intermediate. And this tetrahedral intermediate, when you work up means adding an acid or a base to quench the reaction, or to have a organic product instead of let's say, because here you have a negatively charged species, you might have a positively charged species to balance it out. So for example, you have a sodium plus ion, then you will obtain a salt, but the salt isn't what you want to obtain normally. So you will add some dilute acid, and then you will have your tetrahedral product where you obtain an uncharged species. So yeah, so that's the workup is for. It's for you to get an organic product instead of a salt. Carbonyl addition, nucleophilic attack to carbonyl carbons. We are going to break it down into two steps. So the first step is when the nucleophile attacks the electrophile. So the nucleophile attacks the electrophilic carbon, and then the bond breaks towards oxygen. So that's the first step, and it's called nucleophilic addition. And because there's a lone pair on the oxygen here, the lone pair can actually come down and kick one of the groups out. So it can be either X or Z or Y. So it can kick one of the groups out. So in this case, before we talk about the favorability of the second reaction, the first question we must ask is the first reaction even favorable? So does the first step even occur at all? Does the electrophile react with the nucleophile, and to what extent does it react? And then if there are multiple carbonyl groups, where would this nucleophilic attack happen? Would it happen to all of the carbonyl groups equally, or will it just selectively attack a few carbonyl groups? So this is what we call regioselectivity, or where the reaction would occur. So yeah, so we will form a tetrahedral intermediate where the lone pair on the oxygen can kick out either one of these three groups. So the second step is called elimination. So one group gets kicked out, it might be Y or Z or X. And yeah, so the question we must ask ourselves is this favorable? And which group will get kicked out? Because if we kick out X, isn't it just the reverse of the nucleophilic addition? In other words, if X gets kicked out to a large extent, doesn't that mean that the nucleophilic addition is not very favorable? So yeah, those are questions we must consider. And the group that gets kicked out is called the leaving group. So you might notice that the leaving group looks like a nucleophile also, and that is true because a leaving group is a nucleophile. It is just a good leaving group is just a bad nucleophile. So the leaving group doesn't want to come back. Then that makes it good. So it's a good leaving group, but it means it doesn't want to carry out nucleophilic attacks very favorably. And that means it's a bad nucleophile. So bad nucleophiles are good leaving groups, while good leaving groups are bad nucleophiles. I mean, I'm just repeating. Yeah, so vice versa. Yeah. So I'm going to talk about the first two questions first about nucleophilic addition. So there are some factors affecting the favorability of nucleophilic additions. So the first one is the concentration of a nucleophile and electrophiles, as well as the reactivity of them. So by increasing the concentrations of reactants or decreasing the concentrations of products, the position of equilibrium can be pushed towards the right or towards the product side. So the conversion of the reactants to the products become more favorable. So you will obtain a higher percentage of products overall, and this will increase yield. So if you have to, so because you have your nucleophile and your electrophile, right? So you just need to increase the concentration of one of them in order to push the position of equilibrium towards the right. So for more reactive reactants and less reactive products. So remember last time I talked about how the product will contain an electrophilic part as well as nucleophilic part as well. So if those parts are weaker than the reactants, so the reactants are really good nucleophiles and really good electrophiles, then the position of equilibrium naturally lies towards the right, or the position of equilibrium is really towards the products, so the products are formed really favorably. So let's talk about the reactivity of carbonyl compounds or the electrophiles. So the favorability of reactions depends on the strength of nucleophiles and electrophiles. So some carbonyl groups are more electrophilic than the others, and these will get attacked first. So when you have, like, for example, when your large compound contains multiple carbonyl groups, then the nucleophiles will usually attack the more reactive carbonyl groups first before they attack the less nucleophilic carbonyl groups, or sorry, the less electrophilic carbonyl groups. And when you have those really um like the electrophilicity, if the electrophilicity of some of these carbonyl groups are really low, then it's possible that the nucleophiles don't attack those to a large extent, even if you have unlimited nucleophiles lying around. So yeah, let's talk about nucleophilic additions. So the reactivity of carbonyl compounds, the more commonly seen carbonyl compounds are shown here. So there are several factors affecting electrophilicity of the carbonyl carbon, and those are delocalization effects, inductive effects, and this trend is just a general trend, and the exact sequence depends on the identity of the group, R group. It might be an alkyl group or another group, usually is an alkyl group. Um, and also it depends on the reaction conditions as well as nucleophile use. So what I mean by delocalization effects is basically how many resonance forms can be drawn and what are the weightage of these resonance forms. So for example, Y in ester is not as electrophilic as a ketone is because this lone pair on the oxygen can get delocalized here, while this one pair can go here. So there are two major resonance forms for esters, and because of that, this carbon is not very electron poor, so it's not very electrophilic and it doesn't want to get attacked very easily. So why for an amide this electrophilic carbon is even less electrophilic than an ester is because nitrogen is less electronegative than oxygen. So the inductive effect that pulls the electrons away from the electrophilic carbon is less severe in amides than in esters, and that's why amides are less reactive towards nucleophiles. So for carboxylate, it's even worse because it has a negative charge, so it naturally repels nucleophiles, which are electron rich, because negative and negative will repel each other, and because of that, it doesn't really want to react with nucleophiles very well too. So for the acid anhydride, this is because if you just look at one side, like this carbonyl group, and you have an ester group next to it, so the ester group is electron withdrawing, and it will withdraw the electron density away from this electrophilic carbon, and because of that, this electrophilic carbon will be really reactive and really electrophilic as well, so it attracts a lot of nucleophiles. Of course, acyl chlorides are even more electrophilic because of this chlorine atom here, and it is really electronegative, so it likes to pull electron towards itself and make this carbon really electrophilic. And you might ask, doesn't chlorine have a lone pair of electrons as well? Why can't it delocalize here? Well, the answer is the orbital size. So for the chlorine, the p orbital that is used for delocalization or for used to overlap with the p orbital of the carbon, the electrophilic carbon here. So this p orbital that contains the lone pair in chlorine is a 3p orbital, while this um electrophilic or electron poor p orbital inside this carbon is a 2p orbital. So the sizes are really different. And so the overlap is not as extensive. And if you want to explore this issue further, well, you can Google the orbital, like what orbitals look like, and you will see that for 3p orbitals, sorry, the drawing is a bit ugly. Then you will see that for the 3p orbitals, it actually has a node in between the electron layers. So there's a node in between, and the node is where there's no electron density, and it doesn't want to. So it kind of destroys the overlap, and because of that, yeah, the chlorine atom doesn't share much electron density through delocalization towards the electrophilic carbon. In this case, the inductive effect due to the electronegativity of chlorine wins over and pulls the electron away from the electrophilic carbon, making it more electrophilic and making acyl chloride almost the most reactive carbonyl compound you can find around. So yeah, so these are the factors that you can consider. So, and if you have a molecule with both acyl chloride and ketone groups, then you know that the nucleophile will attack the acyl chloride first. So if you have a compound with acyl chloride and carboxylate groups, then you know that you probably the carboxylate group is not going to react while the acyl chloride group will react almost completely depending on how much nucleophile you have. So because of this reactivity series, because of this reactivity series, it's easier to convert an acyl chloride to a carboxylate ion rather than the other way around. And because of this, yeah, so it's easier to convert one form to another down the reactivity series than the other way around. And because of it's very useful for us to make acyl chlorides. So how can we make acyl chlorides? Well, from alcohol or from a carboxylic acid, we can use isocl2 or PCl3 or PCl5 to convert it to acyl chlorides. So usually in industry, SOCl2 is used because the conversion products are mostly gases and easily separated from intended product, which is the acyl chloride. So yeah, so please take note of these three ways to make acyl chlorides from carboxylic acid or in alcohol. Now let's return to this overview. So we're now going to talk about the favorability, like we're going to continue talking about favorability as well as leaving group ability, which is which group will get kicked out of the tetrahedral intermediate. So usually the lower the nucleophilicity, the better the leaving group. So one thing to tell how nucleophilic a species is to look at the atom bearing the negative charge. So smaller radius, higher charge, and or lowered electronegativity will make it more unstable to bear the negative charge, make it more willing to donate its electron pair, and therefore making it a good nucleophile and a poor leaving group, and vice versa. So one thing we can do is to use the base strength to approximate the nucleophilicity and leaving group ability. So we can take a look at the conjugate acid of the base, and the stronger the conjugate acid, the weaker the base. Well, sometimes the species would prefer to act as a base because the species wants to extract a proton over forming an adduct. So some things to consider are is species particularly bulky? So because of steric hindrance, a bulky species might prefer to extract the proton so it doesn't have to approach the other reactants really closely. So it doesn't need to squeeze past substituents to reach the electrophilic site. So it prefers to extract a proton, which is easier for it to approach. And there are also kinetics versus thermodynamics considerations. So extracting a proton might be faster, but the adducts formed might be more stable. So it depends on your reaction conditions as well. So yeah, what are the reaction conditions, including solvents? So solvents and other reaction conditions such as temperatures will really affect which factor kinetics or thermodynamics wins out. And so reaction conditions are really important for our studies. So whether a reaction is favorable depends on the carbonyl group as well as the nucleophile reactivity. So in this case, you have several reactions shown here. So in the first case, the acyl chlorides react readily with alcohol. So you don't need anything else to help it because acyl chlorides are really, really electrophilic. So it really loves to react with nucleophiles, even though alcohols are not the best nucleophiles because if you have something like if you have a deprotonated alcohol, meaning this, it will become a much stronger nucleophile. But in a case for acyl chloride, because acyl chloride is so electrophilic, it can react readily with alcohols without any external help. So this reaction occurs really readily. Now for the reaction with AC2O, so AC2O is an anhydride. You need the help of pyridine, which is a nucleophilic catalyst or a weak base. So you need its help to make the reaction proceed. But if you use a deprotonated alcohol, because it becomes much more nucleophilic than this alcohol, because the hydrogen is removed, so it becomes much more nucleophilic, so it can react with this anhydride really easily. Yeah, so you don't need the help of pyridine. Now, for this final reaction, it doesn't occur because here you have OET minus, you also have ETOH, but because amides are such poor electrophiles, it doesn't really want to react with alcohols or even deprotonated alcohols, so this reaction doesn't proceed at all. So yeah, it's a really unfavorable reaction. So this doesn't occur to a large extent, or because it's so unfavorable, we just say that it doesn't want to occur. So yeah, so you really need to take a look at the reaction conditions, whether another weak base is or nucleophilic catalyst is readily available to help your reaction. You also need to take a look at how electrophilic and how nucleophilic are your reactants, as well as how stable are your products before you can decide whether a reaction is favorable. So now we're back at looking at a big picture. So um, nucleophilic additions might occur, elimination reactions might occur. So we're going to talk about some reactions where only the first step occurs and elimination doesn't want to occur at all. So the first step, we call it irreversible nucleophilic additions because the reaction basically stops at this step, and you can just do your workup. You can protonate this group, and that will allow you to get your final product, organic product. So yeah, your reaction will stop at this step, the nucleophilic addition step. So we're going to take a look at some examples right now. So addition only, nothing to kick out. For irreversible nucleophilic additions, the position of equilibrium lies towards the far side, far right, which is the product side. And it won't proceed past the addition step because there are no good leading groups. There are no good leading groups in the tetrahedral intermediate. So the electrophile is usually a ketone and or an aldehyde as alkyl groups and H minus are really, really poor leading groups. So we will be talking about reduction with complex metal hydride as well as alkylation with Grignard reagents and alkyl lithiums. So first, with complex metal hydrides. LiAlH4, NaBH4 are all used as a controlled source of H minus ions. So the central atoms are less electronegative than hydrogen, and because of that, the H will carry over the bond pair to attack the electrophilic carbon. So you have an equivalent of H minus. So the free H minus sources such as NaH are not used. So for NaH, the bond between sodium and hydrogen is highly ionic, much more ionic than the bond between Al and H because sodium is much less electronegative than aluminum. So in this case, because of the highly ionic nature, you have H that grabs the bond pair with it. So it has the bond pair with it, and it is too reactive, and it would like to act as a base rather than a nucleophile because it will just grab another H plus ion from somewhere, maybe from the ketone or from another source, and that would just cause it to be destroyed because the hydrogen gas would just fly off. Hydrogen gas because a bond forms between the H minus and H plus ions, and the hydrogen formed would just fly off. And this is super fast and super and hydrogen is super stable, so it will just leave the reaction mixture. And because of that, not only did your nucleophile get destroyed, you also shifted the position of equilibrium towards the left because the reactants are getting removed. And because of that, your reaction becomes very unfavorable, so it wouldn't proceed at all. So yes, so the reason we are using complex metal hydrides is that they have no lone pair. They only have a bond pair. So this bond pair cannot just directly extract protons because this bond pair is still quite covalent in nature. So it doesn't want to directly extract protons. Rather, it wants to approach the electrophile first before reacting, and then it will form an adduct. Yeah, so this second step is basically your workup step where you have an acid, and then this salt thing reacts with your acid to give you your organic product. So note that the second step is carried out when you have used up all this complex metal hydride because if not, this acidic proton might react with your complex metal hydride as well. So during World Cup, you usually remove your excess reactant already, and then you use something that will convert your salt to your organic product and completely stop your reaction. So a more polar bond, such as aluminium and hydrogen, the bond between them will be more polar than boron and the bond between both boron and hydrogen, and that will make the hydrogen there more similar to a free hydride ion and make it more reactive. So NaBH4 is less reactive than LiAlH4. So now we're going to talk about Grignard reagents and alkyl lithiums. So for Grignard reagents, they are basically alkyl magnesium halides. So here, this equation shows how they can be made. So basically, the magnesium inserts itself in between the alkyl group and halogen group, and you will form an alkyl magnesium halide. And this gives you the sorry. This gives you the equivalent of an R minus, just less reactive. So it's So it will react in a controlled manner. So magnesium and lithium are less electronegative than carbon, and that's why the lone pair will be closer to carbon than to magnesium or lithium. The reason you can't use things like sodium is because it will probably be very ionic in nature, and because of that, um, the R minus will be really reactive, and your reaction will be really hard to control. So you can try drawing a similar mechanism for the alkyl lithium. So instead of magnesium halide, you just have your lithium group. So instead of this, you just have a lithium group. Otherwise, the reactions are pretty similar. Yeah, so let's take a look at this mechanism. So this R carries its bond pair over to the electrophilic carbon, and then the bond pair here goes to the oxygen, and the oxygen so this is the anion, this is the cation. So you must always have charge balance in your reaction mixture, and so you have removed the excess reactant, you have removed your excess alkyl magnesium halide. You are going to add some dilute acid or a source of H class ions to your mixture to really stop this reaction. You're going to convert this salt to your organic product, and you're going to remove this. So yeah, you can try drawing a similar mechanism for lithium, um, alkyl lithium. Yeah. So note that this alkyl group can be anything really, and you just have to be able to synthesize it and then use it. So we're going to talk about protic and aprotic solvents. So the two reactions above, so the one with Grignard reagents, as well as the reduction reactions carried out in aprotic solvents. So there are no easy to extract H plus for the nucleophiles to act as bases instead, because as you know, the nucleophiles, some nucleophiles can readily act as bases, and that would really destroy your nucleophiles after they are protonated. So you don't want that to happen. So aprotic solvents are used. So for example, so that just means you are using non-acidic solvents to prevent the good base from getting destroyed via acid-base reactions. So your protic solvents, your common ones are water, alcohol, as well as carboxylic acid. So your aprotic solvents are your ethers, usually your ethers, and you can use those. So ethers are things that look like this. So there are no easy to extract protons. So you're pretty safe using ethers. Okay, now we're going to talk about some reversible nucleophilic additions. That means this whole process, the addition as well as the elimination takes place. It's just during the elimination, instead of the Y minus leaving, you have your X minus leaving to give you back your original electrophile as well as nucleophile. So reversible nucleophilic additions, for these reactions, the position of equilibrium lies towards the left. So it lies towards the reactant side. So this reaction is not very favorable. So it's highly reversible. And the same group that gets added gets kicked out of the tetrahedral intermediate. So some examples are cyanohydrin formation, hydration, both acid and base catalyzed, as well as hemiacetal formation. So can be both acid and base catalyzed as well. So let's talk about cyanohydrin formation first. So your reagents and conditions are your HCN, highly toxic, as well as your KCN in catalytic amounts, so very small amounts. And also cold, because you really want to control your reaction. The reagents and conditions. And yeah, so your nucleophile attacks the electrophilic carbon first, and then uh, this oxygen that's negatively charged can extract a proton from HCN, therefore regenerating the CN minus, and because of this, CN minus is considered a catalyst. So, although we are using this arrow here, the first step is actually reversible. So this lone pair, if you ignore these two arrows, this lone pair can still come down and kick out the Cn minus, and therefore you will get back your reactants. And that's what I mean by reversible. So the first step is reversible because Cn minus is actually a pretty good leading group, and although it's also the nucleophile here, so it's a pretty good leading group, and therefore it likes to get kicked out as well. So yes, first step can be reversed. Now for hydration, these are the acid and base catalysis mechanisms respectively. So for the acid catalysis, by protonating this oxygen, you are making it more electron, you're making this, so the OH group will pull this bond pair more forcefully away from the electrophilic carbon, therefore making the electrophilic carbon more electrophilic. And because of that, water, which is not considered a very good nucleophile normally, it will get to attack the electrophilic carbon here because with the protonated carbonyl oxygen, you are making this carbonyl carbon really electrophilic and really reactive even with water. So after that, your hydrogen can just fall, your H plus can just fall off, giving you your final product. However, the opposite of this reaction can also occur. So for example, you can have your lone pair on oxygen come down, kick out the water, and water is a really good leaving group because it's uncharged. And because of that, this step is reversible. And so acid catalyzed hydration is considered reversible. Now, for the base catalysis, the OH minus is a much more stronger nucleophile than water, so it can attack this carbonyl carbon directly, causing you to form this tetrahedral intermediate. So, just like the acid catalysis, instead of extracting a proton from a water molecule, you can have this lone pair come down and kick out the hydroxide. I know hydroxide is normally not considered a good leading group because it's a good nucleophile. But in this case, you have nothing else you can kick out. The two alkyl groups are very strong bases, so they're not good leading groups, so you can't kick them out at all. So you can just kick out this OH minus group and then form back your reactants. So in both cases, notice that you have added a H plus, you have removed the H plus, so H plus is catalytic. While for the base catalysis, you added a OH minus, you minus the OH minus, and therefore hydroxide ion is catalytic as well. So yes, these are the explanation. Now for hemiacetal formation, you're basically just you're just replacing water with an alcohol, and you're carrying out the same thing as hydration. So the mechanism for acid catalysis, I'll just go through it. So first thing is, of course, making the carbonyl carbon more electrophilic. So you're going to add a H plus here. So your lone pair on oxygen is going to extract this H plus, giving you this. So this compound would be much more reactive than your starting material, which is just a ketone. So you have your ROH, you have your alcohol. R group is just an alcohol group, and then the lone pair on the alcohol will attack this, giving you your Let me use this. I forgot to draw the arrow here. So at this stage, of course, the alcohol can get kicked out. So that will cause this reaction to be reversed. You just have to minus a H plus to give you your final product. So you can draw a mechanism for the base catalysis of hemiacetal formation as well. You can try it as an exercise, and it's pretty similar to the base catalysis for hydration. We're going to talk about addition elimination reactions in another video, and I hope you have enjoyed this video so far. So thank you for watching, and I'll see you soon.